Okay, here we go. Equivalent fractions are an important part of working with fractions. And one of the things that's true about equivalent fractions is that they have the same value. Some examples of fractions that are equivalent to each other. 1/2 has the same value as 2/4. And if you kind of look at that and just think about it for a minute, sure, 1/2, 2/4, we could draw the area model of those and see how they're the same. Um, and if we wanted to have another equivalent fraction, we could say, well, 3/6, that's also a half. All of these have the same value. That's what makes them equivalent fractions. If we wanted to um, write a fraction that is equivalent to 2/7, but has a denominator of 35. So we want to write a fraction that's equivalent to 2/7, but has a denominator of 35. So what we're going to have here then is we want something that's equal to 2/7, but it has a denominator of 35. And a way that we can do this, relatively straightforward, and this is the approach that we'll take, is we look at the denominator and see, well, to get from 7 to 35, that had to be multiplied by 5. If I multiply the denominator by 5 and I want to keep my new fraction equivalent to my old fraction, then I also have to multiply the numerator by 5. And when we do that, 2 times 5 will be 10. And so what we're saying is 2/7 and 10/35 are equivalent to each other. Depending on the problem we're working on, it might be really convenient for us to have this written with 35 as a denominator. And so that's where this comes in handy. Let me know if you have questions on that before I have you try one. Okay. Create a fraction that's equivalent to 3/8 that has a denominator of 72. I'll make a poll for this and let you try it. All right. So create a fraction that's equivalent to 3/8 that has a denominator of 72. So it has the same value as 3/8, but we've written it so that it has a denominator of 72. We'll go another 20 seconds on this and then we'll talk about it. All right, let's see how we did on this one. All right, unanimous. I was hoping for that and we got it. Very good. Okay, let's just look through it just to make sure. So we're going to start out with this fraction that is 3/8. And I want to create a fraction that has a denominator of 72. Well, as I look at this, what did I have to multiply by down here? 8 times what is 72? That's 9. If I multiply the denominator by 9, if I want my fraction to be equivalent, I also multiply my numerator by 9. And so I'll have 27 out of 72. Poll went great. Let me know if you have any questions about that. Reducing fractions. Instead of multiplying the numerator and denominator by the same thing to create an equivalent fraction, we can also reduce fractions. Now, when we reduce fractions, they're equivalent also. If we start out with, say, 30/40 seconds, and we want to write that in as reduced a form as possible, there are a couple of ways you can go here. One approach is to look at it and say, what's the biggest number that will go into 30 that will also go into 42? What would that be? What's the biggest number that will go into 30 that will also go into 42? Very good, Katrina. Stephen, perfect. 6. So what I could do here is then, if I can figure out the biggest number that will go into these, I can divide the top number by 6, divide the bottom number by 6, and wind up with 5/7. And I've reduced that fraction. What I've done here is I've created a fraction that's equivalent to the original, but this time I just wanted to reduce it as much as possible. I wanted to divide as much as possible. If you don't happen to see that 6 is the biggest number that'll go into those right away, that's okay. You can still get to 5/7. If you look at 30/42 and you think, those are both even numbers. So I could just divide the top by 2, divide the bottom by 2, and I've reduced it. I haven't reduced it all the way. I need to keep going, but I have reduced it by dividing those by 2 because they were even numbers, so I knew I could. Now I look at 15 and 21 and I think, hey, 3 will go into both of those. So here we divided by 2. Now we're going to divide by 3. 15 divided by 3 is 5. 21 divided by 3 is 7. And sure enough, we get to the same place. So if you don't happen to see that 6 will go into both of those right away, that's okay. Find something that you do see that will go into both, and then take that step. And then after that, reevaluate and say, hey, can I reduce these anymore? Yeah, I sure can. I could divide them both by 3. Now, once we get to 5/7, we're all done. Let me know if you have any questions on that. Okay, very good. Ordering fractions. Now what we want to do is we want to order these fractions from least to greatest. And if that were 1/3 and 2/3, that would be really easy. Obviously, 2/3 is bigger than 1/3. They have the same denominator. But over here on the left, these 3 fractions I've been given, they don't have the same denominator. That makes them a little bit harder to compare. So what we are going to do is we are going to get a common denominator. So I have to decide what that's going to be. I'm going to rewrite these fractions as equivalent fractions, and I want them all to have the same denominator. So what I want to try to find here is a number that 4 will go into, and 5 will go into, and 6 will go into. Something that all 3 of those will go into. Does anybody have a number that all 3 of those will go into? And if you have one, that's great. If you don't, I have a technique you can use. Austin says 60. Very good. That's exactly right. All 3 of those will go into 60. Laura says 60. Very good. Anybody have something different? Okay, Katrina's at 60. All right, so we're going to go with 60, and then I'm going to show you the other thing in just a minute. But all right, I agree. So we're going to write 3/4 as an equivalent fraction that has 60 in the denominator. Let's see, that's 4 times what would give me 60? Gosh, I don't know. I'm just going to divide it. 60 divided by 4 is 15. So I need to multiply by 15, and 3 times 15 will be 45 in the numerator. If I do anything that you're not sure where the numbers came from, make sure you let me know. So basically what we're saying here is that 3/4 and 45/60 are equivalent. In this particular problem, it's useful for me to rewrite 3/4 with a denominator of 60. So that's exactly what we did there. Now we'll do the same thing with 2/5. let's see, 5 times what would be 60? Yeah, I don't know that one either. I'll do 60 divided by 5 and see that that's 12. So I'm multiplying 5 times 12 to get 60. So we need to multiply that 2 times 12 and get 24. Here again, and I apologize for being redundant, but I just want to make sure that the point is really solid. We're saying that 2/5 and 24/60 are equivalent to each other. They have the same value. In this particular problem, it's useful for me to rewrite 2/5 with 60 as a denominator, so that's what I've done. And then finally, we'll do the same thing with 5/6. We'll rewrite that with 60 as a denominator. That one's easier to see. 6 times 10 will give me 60, so 5 times 10 in the numerator will be 50. Now it's really easy to see which one of these is smallest and which one of these is biggest, and ordering them from least to greatest because they all have the same denominator. So let's see, the one that's the smallest is this one here. That's 24 over 60. And the next biggest is this one, which is 45 over 60. And then finally, the biggest is 50 over 60. Of course, my job in this question was to write these fractions from least to greatest. So now I want to make sure and I do those from least to greatest. Okay, 2/5 was the smallest, 3/4 was next, and 5/6 was next. And then here's my answer, those fractions written from least to greatest. And the way we went about that was just find a common denominator and then use that to figure out which one's the biggest and which one's the smallest. Let me know if you have questions on that. Before we leave this page, I do want to talk to you about finding that common denominator a little bit. But before I do that, I want to see if there's any questions with anything we did there. Okay. So in this case, Katrina and Steven saw, or excuse me, Austin and Laura and Katrina saw that 60 was a number that all these would go into. You might not recognize that right away. There's another way to go here. If you see there's a 4, a 5, and a 6 that are the denominators, if you can't figure out, I don't know what all three of those go into, I can't think of anything. What you can always do is multiply them together. If you just do 4 times 5 times 6, multiply those three denominators together. 4 times 5 times 6 and get 120, that can work as a common denominator. It's not necessarily the lowest common denominator, but that's okay. It's still going to work just fine. Let me show you. So if we want to rewrite each of these with 120 as our denominator, we're going to use that exact same process. 4 times what would give me 120? Let's see. I don't know. I'll divide it. 120 divided by 4, that's 30. So I need to multiply the numerator by 30, and that's 90 over 120. Okay. I want to rewrite 2/5 with 120 in the bottom. I don't know how many times 5 goes into 120, so I'll divide it. 120 divided by 5 is 24. So I'll need to multiply the 2 by 24, and it'll be 48 over 120. And then finally, 6 goes into 120. That's 20 times. 5 times 20 will be 100. And now what I'm doing is I'm comparing these three numbers down here in red. Nothing changes as far as the values go. This one's still the lowest, this one's in the middle, and this one's the highest. I get the exact same answer that way. So if you happen to recognize that all of those will go into 60, great. If you don't, you can just fall back on the fact that if I just multiply those three denominators together, I'm guaranteed to get a number they'll all go into, and that's totally fine. All right, let's have you try one. Order those followings. I'll order those following fractions from least to greatest. 5/8, 2/3, and 7/12. I'll make a poll for this one and have you try it. Put those fractions in order from least to greatest. They don't have a common denominator right away, but if we get a common denominator, then it's really easy to compare them. Let's go another 25 seconds, and then we'll do it together. Okay, let's see how we did on this one. Unanimous again. All right, very good. Okay, I'm curious, since everybody did so well on this one, our working through it will be pretty straightforward. What'd you use as a common denominator for these three fractions? 24, 24. Okay. Anybody multiply them together and use 288? If you did, it's totally fine. Um, yeah, very good, Will. It's totally fine to use 288. Katrina, no problem at all. If you want to use 288, you did just fine there. I do think the 24 kind of jumps out at you in this one with the 8, with the 8 and the 3 and the 12. It sort of, well, 12, the next one would be 24, and 8 and 3 will both go into that. But nothing wrong with using 288. Completely fine. If we use 24 here, we need to rewrite 5/8 with 24 as a denominator. We need to rewrite 2/3 with 24 as a denominator, and 7/12 with 24 as a denominator. If we multiply the denominator by 3, we multiply the numerator by 3, denominator by 8, numerator by 8, and denominator by 2, numerator by 2. Wow, those are all really close together. 14/24, 15/24, and 16/24. But the smallest is 14/24, so that's 7/12. The next smallest is 15/24, so that's 5/8. And so 2/3 must be the biggest. If you use 288 as your denominator, you're going to get these in the exact same order. 7/12, then 5/8, and 2/3 is the biggest. Let me know if you have any questions on that. Poll went great. Okay, here's a similar question, but a little bit different I want you to try. Which one of those numbers is closest to 1/4? We're doing the exact same thing here. We need a common denominator. We want to see which one's closer to 1/4. So we do have three fractions that we're working with, but now it's just which one of those is closer to 1/4. I'll make a poll for this and let you try it. Same idea here, a little more challenging. We're not just putting them smallest to biggest. We're trying to figure out which one of those is closest to 1/4. But the way that we'll do that is get a common denominator across the board, and then we can see how far away they are. Go another 20 seconds, and then we'll talk about this one. Okay, let's see how we did. Okay, strong agreement, but not unanimous and spread across all the answers. So let's be a little careful as we go through this one and you ask any questions that you might have as we do talk through it. So which one is closest to 1/4, 3/8 or 2/5? So we have these three fractions we're concerned with. And just like before, we want a common denominator so that we can make a comparison. Let's see, I need something that 4, 8, and 5 will all go into. Well, I don't know. Nothing's jumping out at me, so I'm just going to multiply them together. 4 times 8 times 5 is 160. Pretty big number, but I'm going to use 160 for my comparison here. Now, if I'm going to rewrite 1/4 with 160 as the denominator, then let's see, 160 divided by 4, that means I multiplied the denominator by 40, so I multiply the numerator by 40, and 40 over 160, that's what I want to figure out what's closest to. All right, 3/8, I'll put 160 in the denominator, and 2/5, I need to put 160 in the denominator. All right, 160 divided by 8, that means we multiplied by 20, and 20 times 3 in the numerator, that's going to be 60 over 160. And then 160 divided by 5, I don't know, 32. So we multiplied top and bottom by 32, so that's 64 over 160. And so the three numbers that I have here that I'm working with are 40 over 160 is what I want to know what's closer to. Well, I have 60 over 160. That's going to be a little bit bigger. And then I have 64 over 160. That's going to be even bigger. So the one of these that's closest to 40 over 160 is the 60 over 160, and that's 3/8. So 3/8 is closer to 1/4 than 2/5 is. And getting a common denominator is how we can compare. If you did this with a denominator that wasn't 160, what'd you use? 80 for Lee, 40 for Stephen. Very good. 40 for Madison. Those all work just as well because we're looking for a number that 4, 8, and 5 will all go into. And 40 works, 80 works, 160 works. So don't feel like there's if I don't pick the wrong denominator, I'm going to mess this up. That's totally not true. Just make sure it's something that 4, 8, and 5 will all go into, and you are just fine. If you want to see it with any of those other denominators, we can do it. If you feel comfortable with it, then maybe we don't need to. Let me know if you have any questions on that. All right, very good. Take a side step for a second and talk about the idea of prime factorization. The idea behind prime factorization is that any number can be written as a product of prime numbers, meaning we can multiply prime numbers together to get there. It's almost like a fingerprint for a number. Any number has a prime factorization that goes with it. Here's an example. Let's look at, say, 84. I want the prime factorization of 84. What I want to do is break this down till it's just prime numbers. A key here is there's more than one way to arrive at the answer. When I see 84, I think even number, so I can multiply by 2. You might remember these as called factor trees at some point. It's kind of what's happening. Is 2 times 42 would give me 84. Now, I can't break down that 2 anymore, but I can break down that 42. It's an even number. So this is going to be 2 times 21. Can't break down the 2, but I can break down that 21 into 3 times 7. And actually, I want to write it as 7 times 3, just for illustration purposes. And once I get to a place where at the end of every one of these strings, I only have prime numbers, nothing will go into it except one in itself, then I have the prime factorization of that number. And then the way that we write the prime factorization is from smallest to greatest. So if you look at this, that you might see 2 times 2 times 3 times 7. And then wherever we can use an exponent, we're going to. So I have 2 2's. So I'm going to rewrite this as 2 squared times 3 times 7. And that is the prime factorization of 84. I've written it as a product, multiply them together, of prime numbers. So product of primes would give me 84. There it is. 2 squared times 3 times 7. Least to greatest, and use exponents when you can. One thing I want to show you with this is I said there can be more than one way to do it. What if you're getting the prime factorization of 84 and you're like, but I didn't see 2 times 42 at first. I saw 4 times 21. Okay, if you saw 4 times 21, that puts you here. That 4 can be broken down into 2 times 2, and the 21 can be broken down into 7 times 3. And we have 2 times 2 times 3 times 7. And we'll use that exponent and get the exact same thing. So it doesn't matter how you break it down. As long as all of your steps are correct, you're going to get to the same place. So don't feel like if you didn't do 2 times 42, your answer is going to be wrong. That's not true. We're breaking this down to a product of prime numbers. There's only one product of primes for each number. And so the prime factorization, you're going to get to the same place no matter how you start. Before we go on to looking at important use of prime factorization, I want to know if you have any questions about what we did there. Okay. Greatest common factor. What the greatest common factor is it's the biggest number that will divide evenly into the two numbers we've been given. So using prime factorization, we are going to find the greatest common factor of 45 and 60. Okay. What I need to do then is I'm going to find the prime factorization of 45 and I'm going to find the prime factorization of 60. As I do this, you let me know if you see anything that you're unsure of or you have questions about. So 45, that looks like 3 times 15, and that looks like 3 times 5. So my prime factorization of 45 is going to be 3 squared times 5. Again, let me know if you see anything that isn't clear or doesn't make sense. Prime factorization of 60. Well, that's an even number, so 2 times 30. And that'll be 3 times 10. And then that'll be 2 times 5. And so what I have there is, let's see, I'll go ahead and be explicit with this one. 2 times 2 times 3 times 5, which is 2 squared times 3 times 5. So on the left over here, I have the prime factorization of 45. On the right, I have the prime factorization of 60. I'm looking for the greatest common factor. What is the biggest number that will go evenly into those two numbers? And what I'm looking for here then, when I'm looking for the greatest common factor, is I'm going to keep whatever they have in common. When I look at the prime factorization, whatever they have in common, that's what I'm going to keep. So I'm looking at these two numbers, and just starting with the smallest possible number that I have, I've got 2 squared over here, but I don't have any 2's over there, so I'm not going to keep that at all. I have a 3 to the first power and a 3 to the second power. What they have in common, where they overlap, is just a 3 to the first power. So I'm only keeping 3. I'm not keeping 3 to the second power. Yes, it's true that 45 does have 3 2's in the prime factorization, but 60 only has 1. I'm keeping what they have in common and the overlap, the intersection, if you will. And then let's see, there's a 5 over here and there's a 5 over here. So I'm going to keep a 5. And then I'm going to multiply those together and get 15. And the greatest common factor of 45 and 60, the biggest number that will go into those evenly is 15. Keep in mind, yes, I use this 5, and yes, I use this 5. There's only one 5 in this prime factorization. There's only one 5 in this prime factorization. So when I go to find the greatest common factor, I only use one 5. Because what they have in common is 1, 5. Let me know if you have any questions on that before I have you try one. All right. Find the greatest common factor of 36 and 90. I'll make a poll for this and let you try it. So what we're after here is the biggest number that will go into 36 that will also go into 90. And the way we do it is we find the prime factorization of each number and then keep what they have in common and multiply those things together. I'll give you some time on this. There's no rush. Greatest common factor problems are very common. I don't mean to pun there, but these are definitely the kind of thing you can expect to see in practice problems on a quiz, on an exam. Let's go another 30 seconds, and then we'll talk about this one together. Okay, let's see how we did on this one. Okay, strong agreement, not unanimous. So let's be careful as we do this one. Probably, my guess is the prime factorization went fine. It's deciding what to do with those numbers after you get them that might be the challenging part here. You can correct me if I'm wrong and you ask whatever questions you might have. So I need the prime factorization of 36. Well, let's see, that's 6 times 6. And this one will be 2 times 3, and this one will be 2 times 3. And I have 2 times 2 times 3 times 3, which I can write as 2 squared times 3 squared. So there's my prime factorization of 36. If anything in there doesn't make sense to you, make sure you ask about it. Then I need to do 90, and I don't know, 9 times 10. And that might not be the way you saw either of those. Hopefully you got to the same place anyway. And then 9 is 3 times 3. 10 is 2 times 5. So this is going to be 2 times 3 squared times 5. And those are my prime factorizations. Now we have to figure out what to use to find our greatest common factor. And what we're going to do is we're going to keep what they have in common. We're looking for the overlap, whatever they have in common. Over here I have 2 squared. Over here I have 2 to the first. So what they both have is just a 2 to the first. Over here I have 3 squared. Over here I have 3 squared. So they both have 3 squared. And I'm all out on the 36. Yes, the 90 has a 5, but the 36 doesn't have a 5 in it, so I'm not going to use that. And now I'm just going to multiply these together. And let's see, that's 2 times 9, or 18. So our greatest common factor there is 18. Let me know if you have any questions about how we chose those numbers, if it's not clear at this point. And what we're saying here is the biggest number that will go into 36 evenly, that will also go into 90 evenly, is 18. That's greatest common factor. All right, very good. We did some problem solving on Monday using the area model. We're going to revisit that a little bit today. And this might sound familiar. There was a grove of trees in the forest. Fungus infected 1/3 of them, damaging the wood. Of the remaining trees, loggers came in and cut down 2/5 of those. What fraction of the original grove remains? On Monday, when we did a problem similar to this, we were told how many trees were left and asked how many were in the forest at the beginning. This is the similar setup, but a different question that we're being asked. What fraction of the original grove remains? Our approach is going to be very similar to what we did on Monday. We're going to draw a picture of the forest as a rectangle, so we can use the area model to solve. Fungus infected 1/3, so I'm going to section this off into thirds, and then this is what was infected by fungus. Of the remaining trees, loggers cut down 2/5 of those. So now I'm going to cut this into fifths the other way. Hopefully this is relatively comfortable. If you hadn't had a chance to practice much yet, that's okay. Hopefully this looks like, okay, yeah, I see what's happening here. And then the loggers cut down 2/5 of those. So when the loggers came in, they cut down 2/5 of the remaining trees. There's 1/5, 2/5. And so now we're done with all our shading, and we just have to answer that question. What fraction of the original grove remains? We just need to figure out how many pieces there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 total pieces. And the trees that remain, there's 1, 2, 3, 4, 5, 6. So the fraction that remains is 6 out of 15 pieces, or 6/15. That could be reduced. So we'll go ahead and reduce it. Let's see, 3 will go into both of those. So if I divide the top by 3 and the bottom by 3, 2/5 of the original forest remains. Let me know if you have any questions about that. Essentially, it's the same process we did on Monday, but a different type of question. So we have to be prepared to think about how we're going to answer it, and then answer it that way. Okay, if that's comfortable for you, then you're doing really good with the problem solving using the area model, and that's great. Okay. Another problem solving. You started cooking a meal at 5 p.m. and it will be done at 7:30 p.m. When it's 6 p.m., what fraction of the cooking time remains? So this is similar to the last question where it says, what fraction remains? Instead of the area model here, for this one, I'm going to do this using the length model. So I'm going to go ahead and set up a sort of a number line kind of thing here where, all right, let's see. I'm going to start cooking at 5. I'm going to finish at 7:30. I think it's going to be easier for me if I just go ahead and make this 8 so I have whole numbers, because then I'll have 6 right here and I'll have 7 right here. And then 7:30 here is what I care about. I went all the way to 8 just so I could make the marks easier. So there's nothing magic about 8. You can go all the way to 10 if you want to and do 5, 6, 7, 8, 9, 10. Just realize that 7:30 is going to be an important number for us. Okay, then. My question here says, at 6 p.m., what fraction of the cooking time remains? So it's 6 p.m. right here on my length model, if I want to look at it that way. And if I want to chop this thing up, the fact that this is at 7:30 means I want to make sure I cut this up into 30-minute intervals, not just hours. So I'm going to go ahead and put 6:30 in here, and I'm going to go ahead and put 5:30 in here. And then when I look at this and I say, okay, well, the whole cooking time, I started at 5 and I'll be done at 7:30. So the whole cooking time is 1, 2, 3, 4, 5 pieces along my length model. And how much of that remains? Well, given the fact that I'm at 6 o'clock here, I still have this one, and this one to go. So I have 3 out of the 5 pieces of my length model remaining. And so what fraction of the cooking time remains? 3/5 of the cooking time remains. Beautiful use of the length model to solve a problem like this one, where we can kind of draw it out and just use the picture to say, well, if it's 6 o'clock, then I have 1, 2, 3 of the 5 pieces remaining. Let me know if you have questions on that before I have you try one that's similar. All right, here goes. You started cooking a meal at 5 p.m. and it will be done at 7:30 p.m. At 7:15 p.m., what fraction of the cooking time remains? Because 7:15 is in there, we're going to want to cut this into 15-minute intervals. I'll stop after that and I'll set up a poll for you to try this one. If you get an answer that's none of those, choose the one that's closest to yours, and then follow us through it, and we'll see if we can clear up any issues you might have had. Go another 25 seconds, then we'll talk about it. Let's see how we did. Okay, not unanimous, but strong agreement. That's good. There are a couple different ways you can solve this, and I'm going to go ahead and talk about both of those here. First, we're going to do the length model like we did in our example. So in using the length model here, you can set up kind of a number line to use as your length model. And I'm starting at 5, and I want to go to 730. You could do 730, but I'm going to go ahead and do 8 just because it's easier for me to put 6 in here and 7 in here. And then I want to chop this up into 15-minute pieces because 7:15 is what I care about. So 7:15, 30, 45, and keeping in mind that right here at 7:15 is a really important number. And then 15, 30, 45, 15, 30, 45. And then also an important number is that we're going to be done right here at 7:30. Okay, so we'll just count them up and see how many we have all together. It looks like all together I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 of those 15-minute intervals. And if I'm here at 7:15, then I only have 1 left. So of the 10 that are left, I only have 1 still to go. So what fraction of the cooking time remains? 1/10. And that's doing with the length model. And I really like that. You don't have to manipulate numbers very much. You're just using a picture to solve it. I think it's great. Some of you might prefer to do this with a more of a numerical approach, and that's totally fine. At the very beginning of the semester, we talked about the fact that there can be more than one way to do things. And as long as your way is valid and repeatable, it's fine. What you might have said here is, well, if I start at 5 and go to 7:30, that's 2.5 hours. And I can see that it's 7:15, so what I have left is 15 minutes. I need to use the same unit here. I can't have hours for one thing and minutes for the other, so let's turn this all into minutes. So 2.5 hours would be, let's see, 2.5 times 60, that's going to be 150 minutes. So it's 150 minutes total cooking time, and I have 15 minutes left. So when I'm asked what fraction remains, that's 15 minutes out of the 150 minutes. Well, we can reduce that. 15 will go into both of those once, 10 times, and 1/10 of the cooking time remains. If you like the length model, I think it's a great way to solve this. If you're like, I'm just going to use numbers, if that's all right with you, it's perfectly all right with me. Just make sure you're careful with those and make sure you work in the same units. You don't want to put 15 over 2.5. That'd goof things up. Let me know if you have any questions on that one. Okay. Just a couple of homework notes before we put the finishing touches on section 2.2. Number 48 and number 50 in your practice problems, those are very abstract looking problems. And they're kind of hard to do that way. When we're given something that's abstract and we're trying to make sense of it, a great way to help make sense of it is put numbers in and see what happens. That's the advice I'll give you on that. I'll leave you with it there, but if you're having trouble making sense of it with the variables in an abstract way, put some numbers in and that'll help you make sense of it.